Okay, I think we are ready to start. So welcome to this 8th webinar of the Royal Academy of Engineering's technical briefing series, aimed at demystifying technical subjects in which our fellows are experts. Recordings of all previous seminars are available to view on the website, and the Academy staff are going to put the link in the chat, and we'll also email it to you all tomorrow, along with the link to the recording of today. My name's Julian Allwood. I'm Professor of Engineering and the Environment in the University of Cambridge. And for 20 years, I've led a group working on industrial decarbonisation, particularly focusing on the demand side with material and resource efficiency. And our work has made it absolutely clear that electrifying industrial heat is a central plank of a decarbonised future industrial system. So it's a really hot topic and one I'm very much looking forward to learn more from Rob. Just to cover a couple of points of housekeeping, the webinar is being recorded. And while the talk is going on and afterwards, please add your questions to the Q&A function, and I will run through those with Rob and get through as many of them as we can in the time allotted to discussion. Rob Savidge has had a very distinguished career with Rolls-Royce, including leadership of engine and technology programs, leading to eventually becoming Director of Technical Assurance for Rolls. In 2023, Rob left Rolls to join Coolbrook I don't know how to pronounce it, as Director of Engineering. And they, of course, are a technology company developing the capability to decarbonise heavy industry through supplying high-temperature all-electric heat. Rob has been recognised as a McRobert Award finalist as part of the team developing the Trent 900 aero engine, won the Von Karman Award for his contribution to the AE 380 programme, and the Royal Aeronautical Society Team Gold Medal, also for the Trent 900 medal. So we are in the company of a very distinguished expert talking about a topic of great interest, and I can't wait to hear more. Rob, over to you.
Okay, thanks, Julian, and a big thank you to everybody for joining this briefing this morning. I think just to finish off Julian's little introduction, this is a complete change of technology for me. What I'm working on now doesn't have to fly, doesn't leave the ground, fortunately, but it's a very, very, I should say, aligned technology with my experience. I'm the Director of Engineering at Coolbrook Technologies. There's the Coolbrook HQ is in Helsinki, and we now have Coolbrook Technologies, which is a UK limited company, and over half the Coolbrook company is now based in the UK and divided between an office we have in Leicester and an office we have in Oxford. Okay, next slide, please, Nish. So what is Coolbrook aiming to do? Well, let me just give 2 minutes on Coolbrook as a company. Coolbrook as a company was started in 2011, and it was on the back of some conversations between scientists who'd identified that there was a technology that had started to be developed in the late 1990s by some scientists, and recognised that there could be a potential application of this in providing heat for heavy industry. And the whole business case for the company was based on 4 points. And the first was that of burning fossil fuels is a major source of CO2 emissions. And as a world, we need to stop that. And I think the trajectory we're on at the moment is it's not happening fast enough. It's clear that energy intensive industries have not reduced at a fast enough pace, and we've got to accelerate the decarbonisation. Many industries are now moving towards electrification. And one of the key challenges that was recognised was that there was no electric technologies that were available to produce sufficient temperatures for the key industrial processes. And coupled with that, we need to start utilising more green electricity that comes from renewable sources. And that's really also supporting just geographical and governmental initiatives to grow the amount of renewable energy that we use. There are other solutions to potentially address this issue. They are quite expensive, and also at this point in time, they lack the required scale. So it's recognised that new innovation was needed, and the Coolbrook company was formed to develop this technology that had been identified to reduce CO2 emissions. And that's an annual reduction of somewhere around 2 gigatons through electrification of hard-to-abate industrial sectors. Okay, next chart, please. Now, this technology is a combination of rocket science, and the initial thoughts about this technology came from rocket motor engineers. And then that was coupled with the application of turbomachinery and thinking about how turbomachinery operates, and then looking at applying that to chemical engineering and actually more broadly to wider industrial engineering in terms of cement production and steel production. And as it happens, as we're now starting to develop our understanding of the marketplace for this technology, many other processes that are sort of identified as an opportunity. Okay, next chart, please, Nish. So the proposition here is that we take renewable energy, and that may be wind power, it may be solar power, it could be nuclear power, and drive an electric motor to drive a piece of machinery that transfers the electric energy into effectively air or a working fluid, and thereby producing that hot air or hot working fluid in an entirely green way. In the background on this chart, you can see today it's most of that is done by burning fossil fuels. That's whether it's oil, coal, or actually waste is used quite heavily in industry to provide heat. The technology has potential to go up to temperatures of around 1700 degrees C. That technology is part of the journey that we're on to get to that temperature. And we're starting the journey at lower temperatures in some straightforward applications, I think, to de-risk the engineering of the integration into those industrial processes. So next chart, please, Nish. So who are we working with on this technology? The design of this technology is really founded on aerodynamic design, and it's actually turbomachinery. And the initial aerodynamic designs for this turbomachinery have been worked on together with Cambridge University and with Oxford University. We're working very closely with Brightland in the Netherlands, which is a petrochemical technology development site, and also the Ghent University, who work very closely in the petrochemical industry. Our aim is to build scale to manufacture and deliver this technology and engineering companies. We've partnered with ABB, who were keen to join this journey and provide the electric motors and the electrical control system to drive these machines. We've also partnered with Linde, who are a big petrochemical integration company, and also Schmid-Stack, who assist in that integration with heat exchangers. So how are we getting into the market? We're identifying now use cases for this technology. Some of the prime customers who we are working very closely with, we've done integration studies and are working towards signing agreements for the first application. One there is Shell, who are very interested in the cracker for hydrocarbon cracking in the plastics feedstock industry. Same goes for Braskem too, and Savidge. We're working very closely with Ultratech Cement, which is, I think it is the biggest cement company in India. They produce around 200 million tons of cement a year, which is an absolutely amazing amount of cement, not of it of which is exported, but all of which is produced by burning fossil fuel. We're also working again with Cemex, a cement company, and ArcelorMittal, who is a steel company, who again are very interested in this technology for a number of applications in the steel and metal industry. Okay, next chart then, please, Nish. So what's the opportunity here? Our rotordynamic technology has got huge potential to cut CO2 emissions. In the chemicals and petrochemical industry, this is replacing gas in the steam cracking process, where natural gas gets burnt at the minute, and also looking at hydrogen production and methanol production from natural gas or biogas. I think one of the interesting statistics, which isn't immediately obvious on here, that 500 million tons of CO2 a year is half the annual CO2 emissions from aerospace industry. So it's a pretty big opportunity, and one of which we're pretty excited to be part of, hopefully providing a solution for. Iron and steel industry, they use a lot of air in preheating, in blast furnace, and provision of heat for hydrogen-based reduction processes, which we're working on closely with the steel industry, and also heating for hot rollings, casting, coking and sintering. And that is an opportunity of around about 600 million tons of CO2 a year. The cement industry, as I mentioned earlier, burn an awful lot of fossil fuel, and also is basically municipal waste, and replacing those with electric heating in the kilns. Currently, the emissions from the cement industry are about 1,000 million tons of CO2 a year. As I mentioned earlier, there are quite a few other industries that need hot air or hot gas, which we're now identifying. And they're really just serving to demonstrate the potential of this technology to be applicable in, I would say, a much wider range of industries than we'd first anticipated. This in total has the potential to reduce global CO2 emissions by about 2.4 gigatons. And that's about 240 billion euros at 100 euros per ton of CO2. So it's a huge opportunity which we're driving at here. Okay, next chart, please, Nish. So what does this machinery look like? It's essentially an electrically driven heater, and this heater is based on turbomachinery. And putting it simply, and I'm going to talk a little bit more about the detail of this in a minute, it's an extremely, or the most inefficient compressor that you can design for compressing gas. The potential of it is to heat gases up to 1700 degrees C, those higher temperatures clearly bring the challenge of managing to keep the operating components cool and not melting under the high temperatures. But it's well within the realms of existing technology that's flying around the skies today. Currently, competing electric technology, if you go and look at electric resistance heaters, they sort of run out of temperature capability of somewhere between 600 and 700 degrees C. It's a highly efficient process. We've calculated the efficiency of this process, and it's somewhere around about 90% efficient. And clearly, if you've got 100% renewable energy, you can reduce the CO2 emissions by 100%. So that's the heater. In the reactor, the proposal here is that we have an electrically driven reactor. This uses the same aerodynamic principles as the heater. But what we're doing is replacing the fossil-fired heat exchanger tubes with actually a cracker where the hydrocarbon and steam mixture actually passes through the turbomachinery of this equipment. One of the key technical features of this is you get very rapid heating in the turbomachinery and very short residence time. One of the challenges in the petrochemical industry is with the tube heat exchangers and crackers is that there's very long residence times. You get lots of side reactions happening, and it impacts the yield significantly. Our initial assessments around the cracking process in the rotordynamic reactor suggest that the yield could be up to 20% higher when cracking naphtha to produce ethylene. I think also, and I'll show some more examples of this later, but the capex and opex of this rotordynamic reactor are significantly less than the current equipment. And of course, there's a 100% reduction opportunity here in reducing emissions from steam cracking process. Okay, next chart, please. So where are we with demonstrating this technology? On the right-hand side here, there's a picture of our test facility at Brightlands in the Netherlands. And to date, we've demonstrated heating air to 1,000 degrees C with this pilot rig. The rig is powered by a 0.8 kilowatt, 800 kilowatt electric motor. And it's a scale of the large scale product. And this is really proving the aerodynamic capability of this turbomachinery to heat air. We're now just in the process of reconfiguring that test cell to feed this machinery with naphtha to actually crack hydrocarbons, produce ethylene, and demonstrate the efficiency of this process and understand the aerodynamic characteristics of the cracking process in this unique technology. The whole project cost around 12 million and it is proceeding at pace in really demonstrating the credibility of this turbomachinery technology and the potential to deliver our goals in reducing CO2 emissions. Okay, next chart, please, Nish. So what happens if you take today's process? I'm not sure, can they see my pointer, Nish, or not? I'm not sure whether you can. But on the left of this chart is today's process, and the sort of right-hand picture where you can see the thick black wobbly lines, sorry, on the left-hand picture, on the right, on the tube. You can see carbon builds up very rapidly. These reaction tubes have to be cleaned regularly, and that's in the order of every sort of 7 to 10 days. They have to be flushed out to clean the carbon out. One of the problems here is that the external temperature on those tubes, in order to drive the reaction internally, has to be significantly higher than the required temperature for the reaction. And as a consequence of that, you get carbon buildup on the inside. If I move over to the right, which is a sort of a similar diagram that shows the whole system. If you just click on the bottom there, please, Nish, where it says by click, what we're proposing doing is removing those serpentine reaction tubes and replacing them with a rotordynamic reactor, where the steam and the hydrocarbon is passed directly through the turbomachinery in the heater. And the big advantage here is that it's a very short residence time, so there's a much lower opportunity for side reactions to happen, which generate unwanted byproducts, and therefore you end up with a higher yield in the process, and also lower maintenance. We're hoping to demonstrate this process, as I said, in the Netherlands, and one of the key points we'll be examining is there any carbon buildup in this turbomachinery, and if so, at what rate? How does it impact performance? And also, are we able to shed it through natural means? Okay, next chart then, please, Nish. So what does this look like inside? I've sort of put in here a little bit of detail. Starting on the left, there's a set of rotor blades, and those rotor blades are designed to be an impulse compressor. And those rotor blades are effectively accelerating the air to supersonic speed. And at the same time, they're also raising the pressure. The pressure ratio across those blades is somewhere around about 4:1. But then what we do is we accelerate the air out of the rotor blades and then expand it through a diffuser to convert all the kinetic energy into heat. Now, there's only a single stage of rotor blades in this machine, but what there is around the outside of the turbomachinery is what we call a donut. And the gas takes a helical toroidal path round this donut and ends up having multiple passes through the rotor until such point as it's passed round 180 degrees of the annulus, and then it's exited from the turbomachinery. So each time the working fluid, and whether that working fluid is steam and hydrocarbon or whether it's air, nitrogen, CO2, any working fluid, its temperature increases. And as I said on an earlier chart, we've now demonstrated that this works effectively and have heated air up to 1,000 degrees C. We've heated CO2 up to 800 degrees C. The chart on the right-hand side just attempts to show how the fluid temperature changes with flow path length, or effectively the number of passes around the donut. And as you can see, there's sort of a jagged line up the left-hand side there. As each pass, the temperature increases. Now, one of the interesting characteristics of this piece of turbomachinery is that the rotor blades only see the average temperature between the inlet and outlet. So if I wanted to operate this machine to heat air to 1,000 degrees C, the average temperature of those rotor blades is only around about 500 degrees C. So if I think about material capability and how that might impact this machine, if I wanted to run this machine at, say, 1,300 degrees C, the rotor blades are still only at sort of 650, 700, which is in the realms of fairly readily available low technology materials, and they'll be able to survive without cooling. Other turbo machinery that operates in a similar way, at those temperatures at 1,300 degrees C, you have to start cooling them in some way to ensure that they have adequate life. Okay, next chart then, please, Nish. And I've probably sort of spoken about most of this, but the aim of this RDR concept is to increase the yield of the primary product, minimizing the secondary products, and also minimizing coke deposition. We can very carefully control the residence time by tuning the number of passes in the donut area, in the veinless space, and also maintaining a low hydrocarbon partial pressure with the steam that goes through the process, and also increasing the process temperature in a very controlled way by controlling the speed of the machine. The energy process in this is done through direct mechanical energy transfer from the electric motor. There's clearly a high degree of controllability in this. And as I said previously, the low residence time, high yield, and an unfavourable environment for coking, given the rotational speeds. Okay, next chart, Nish. I'm conscious of time. Well, I know we've got sort of about 3 minutes left, but I just put this in here so that people could get a feel for the size of the equipment. On the left-hand side here, it shows a picture of a cracking system that's got a radiant section on the left that's powered by natural gas. The equivalent heat and cracking flow can be produced by the Coolbrook turbomachinery, which is shown on the right. It's significantly smaller. And the picture on the right there just goes to show exactly what the machinery looks like. A big part of this equipment is the electric motor, the e-house that will house the variable speed control and the electrical equipment, and it obviously needs a transformer too. The rough power of these crackers, we're looking at designing a 10 megawatt one and a 20 megawatt one. The sort of most of the crackers currently in service today are around about 20 megawatt size, but there are a number of applications that need 10 megawatts. But petrochemical companies have got desires to go to 40 and 50 megawatts. So there's potential to grow and scale this as well. Next chart, please, Nish. Okay, so where are we on this journey? You probably picked that up as I've gone through. We're at the end of 2023. We've run the pilot test in the Netherlands in heating air. We're just about to crack hydrocarbons in it. We've launched the detailed design now of our first 7 megawatt air heater, which we're hoping in the next few months we'll take the first orders for. And interestingly, one of those is in a mining application. The other one is in the cement industry. We're building at a very rapid rate a network of partners, potential customers, and our intention that as we go into 2025, we will deliver and install the first heater at the first customer site and demonstrate the true potential of this technology. Okay, Nish, next chart, please. I put this in here. I'm conscious we're running out of time, but one of the competing technologies is green hydrogen. We have done a lot of work at looking at the efficiencies of competing technologies. Hydrogen is probably the closest one that is close to being available at scale. One of the issues with using hydrogen for these processes we're trying to address is the energy efficiency. By the time you've sort of taken the electricity production, which can obviously be renewable through an electrolyzer, transported it, it's only around about 60% efficient. Our energy efficient transfer in the turbo machinery is somewhere around about 90%. The hydrogen process, there's obviously a higher capital investment too. Okay, next chart, please, Nish. Okay, This is just a summary chart. I'm probably not going to talk through this. You might just want to leave this on the screen, Nish, while I think we go over to questions, and Julian is going to manage that process for me. Over to you, I think, Julian.
Well, terrific. Thank you very much indeed, Rob. I think I can imagine a whole raft of questions there. I've written down some of the ones that occurred to me. I can see people have started posting in the chat. So please do take this opportunity to quiz Rob in more detail. Rob, maybe I could ask the first question and just ask for a bit more detail of the second stage of the process. I understood how the rotor accelerated the air, but then I lost it. You said the kinetic energy was converted to heat. What was the mechanism for doing that?
It's effectively you're diffusing and expanding the air. And by doing that, you convert the kinetic energy into thermal energy, and then it passes round that process multiple times.
Okay, and it's so is the exit gas at pressure, or is it back to ambient pressure by the time?
It's back to ambient. That's one of the very different things about this machinery. There is no pressure increase from inlet to outlet, which is sort of interesting, and it's a completely different world to the one I'm used to operating in.
Yeah. Terrific. We've got 3 questions from Gavin Viknaraja, which I think refer to the rotordynamic heater. So the first one was, what's the typical power range requirement in megawatts? And I think you've probably answered that. Then how do the OPEX costs currently stack up against the current normal process, and how will costs reduce over time?
Well, the sort of business case for this technology is primarily based on reducing CO2 emissions and the cost of per ton of CO2 emitted. But it also, for some industries, and an example here is the cement industry in India. They would love to export their cement, but because of the carbon emissions charges to export it, it just means they're just not competitive, and they can't export it at a cost that would make it financially viable for them to do that. So I mean, the other interesting point is that Ultratech have got a 16 megawatt solar field which they're planning to hook up to their 10 megawatt electric motor that drives the system, and in the next 2 years they're doubling that to 30 megawatts. So it's an interesting proposition.
Maybe I could follow up on that. With both the blast furnace and the cement kiln, then you're tackling the combustion engine emissions from generating heat, but not the process emissions. And if we take zero emissions seriously, then both of those processes have to shut, because in both cases, the process emissions are at least the same, if not greater than the emissions from heat. So I was wondering to what extent those are the right application, or whether it would be better to focus, as you have done, on steam cracking, because at least for some plastics, then this would create the first zero emissions route.
Yeah, so we're trying to address it on all fronts, Julian. We're already talking with 2 global cement companies who are designing a process to capture CO2 and use CCS from cement production. And what they're wanting to do is to use our heater to recycle that CO2 and heat the CO2 to heat the furnace to produce green cement. So the answer is it's being thought about, and we got another meeting with one of those companies in a few weeks' time, actually, who are seriously looking at doing that. One of the questions I have of the cement company, and I don't understand, I'm not sure where they're going to store all the CO2 that they capture, because they won't be able to use it all to heat the furnace. One of the options I know is to use it in the cement manufacturing process, where you bubble CO2 back through setting cement, and it improves the strength, I believe, by about 20%. We did actually have a there's a short presentation from somebody at one of the Royal Academy meetings, I think, on that.
Yeah.
So in answer to your question, it's a valid question, but the cement industry is already looking at how they address that to make CO2 free cement.
It'll be interesting if they ever do it. They've talked about CCS for 30 years and not done it. Let's see whether they ever do actually deliver.
Yeah. Sorry, you got a question about the plastics industry. No, it's just a comment, wasn't it?
It's just a comment that I thought that might be a more obvious immediate application.
Yeah.
Philip Hutchinson asks if the price per unit of heat will be high compared with burning gas.
Well, that all depends on the local cost of electricity, and also how much of the electricity is generated by renewable means. But we have done an awful lot of work studying the different use cases in the different geographical locations and in different industries around the world. And there's very definitely a business case for doing this when you take into account the cost of CO2 production. Is the answer. And in particular, if you look in some countries, we're working with a mining company in Finland where the cost of electricity is less than the cost of gas.
Yeah, there's no question that Scandinavia is the place to develop electrical industrial technologies at the moment.
Yeah.
Brilliant. Thank you. The next question, does the heater have applications at lower temperatures? And perhaps I could generalize that to ask you how the efficiency curve varies with temperature.
Yeah, the answer is yes. As you slow these machines down, what happens in the first instance, because the aerodynamics in the turbomachinery is choked, and as you pull the speed back, the temperature drops, but the flow remains. And it's only when you get down to sort of somewhere between 30 and 40% of operating speed that you start to lose the flow. So the answer is they can operate at lower temperatures. Clearly at lower temperatures there are competing technologies in terms of electrical resistance heaters, but having said that, it is amazing the number of companies that are already talking to us that want to use this technology at lower temperatures, making things like tissue paper and all sorts of things which you'd never thought of.
Interesting. Okay. The next one is how small scale could the technology, or if I translate that, I think it's, can you scale this down to small size? So, for example, could it go into a mobile industrial vehicle as an alternative to hydrogen combustion or hydrogen fuel cell electric vehicles?
The answer is it is scalable. Our analysis so far is looking at, how small do you want to make the blades in these machines? The machines that we're currently designing have got a blade height of around about 25 millimeters. You could go smaller and reduce the power. The one that I showed you the picture of that we're running in the Netherlands is 800 kilowatts, and that's sort of about 0.7 meters diameter. So it's not a particular big thing at that power. So the answer is it does scale down.
Okay. Malcolm Brinded has asked a rather good multi-part question. I'm going to break it up. So the first one is, this is terrific. How strong is the IP?
The IP, we have 16 core patents on this technology. The rotodynamic reactor stroke heater is unique. There is no competitor with technology that looks anything like that. And as I mentioned earlier, the big advantages is the average rotor temperature. When you want to go to higher temperatures, it makes life so much easier. And scaling this up, the time scale for scaling up to 10 megawatts is the power of this first air heater that we are now currently into detailed design. We've finished the concept design, we've ordered the first long lead time items, and that first machine will be delivered at the end of next year. We're already planning scale-ups of that. Clearly, we can run 2 machines in parallel with a twin output gearbox and a bigger motor if we needed to, but it's more effective to scale the thing up to a larger size. One of the challenges we're faced at the minute is the variety of use cases and how you cater for those variety of use cases with a small number of machines, because it won't be cost effective to do point designs and provide machines for specific industries. We need to try and create a product portfolio that will address as many of these industries as they can, maybe with some additional technology that allows us to vary mass flow and or temperature at the same time.
Yeah, it seems to me that you've got a strong case for scaling up rapidly because you're producing a hot gas, which is a familiar input to existing processes. So the scale of societal risk is lower, but nevertheless, the most of the receivers of the hot gas are going to have to modify their equipment. So I don't know whether you can retrofit this to a cement kiln or whether you'd have to build a new one to be able to do it.
Yeah, I mean, in the first instance, in the cement industry, we are looking at integrating this into pre-calciners. For those of you who know the cement industry, I don't profess to be an expert, but there are drying applications and pre-furnace heating requirements that this technology does integrate into quite easily, providing the heat for a rotary furnace is on a pretty major scale. So the initial machines that we're looking at, the ideal temperature for these sort of pre-furnace applications in pre-calciners is sort of somewhere between 1,000 and 1,200 degrees C, at around about 20 megawatts. And there's lots of applications at that size with relatively easy sort of integration in today's processes. How are we de-risking? Well, I think one of the key things is the Brightlands project, which showed you a picture of. We have now proven the technology, it works, and we've heated air to 1,000 degrees C. So the next stage is scaling it up, producing a full-scale machine.
Terrific. Let me insert one of my own then, because I'm very interested in electric arc furnaces at the moment, as that's one of the things we've been both promoting and delighted to see them growing in the UK and also exploiting as a way of making cement. If we're going to recycle steel with this, we're going to need pretty much all the temperature you can give us. So we're going to need at least 1,600 degrees to do that. Has anybody started looking at what a steel recycling process powered by this might look like?
In truth, I don't know. We are talking with steel manufacturers for producing raw steel. We're also talking with aluminium producers as well. So in truth, I don't know the answer to that question, Julian.
It would be really interesting to think about what it looks like, because it's a totally different approach to heating old steel. I imagine one of the benefits of the electric arc furnace is that it cuts through a lot of the contaminants that are there. It would be really interesting to know what the efficiency looks like. So whenever you're wanting to sponsor a really interesting research project, then I'll give you my number.
Yeah, okay. I mean, one of the things that the steel industry is talking to us about is heating hydrogen to 1,500, 1,600 degrees C to you get sort of CO2 free steel in the reduction process.
But with a huge electricity requirement. Andrew Churchill says, have you thought about partnering with other zero carbon technologies such as Rolls-Royce's SMRs?
Yeah, and I answered this question in our preamble earlier, but I mean, a typical cracker installation is a string of 14 crackers, like the one I showed in the picture. If you add the power requirement together for those 14 crackers, it equals approximately the power of an SMR. And I do know, because I've bumped into somebody who I know is very close to the SMR program, and they are talking to Shell about that. And clearly, we could integrate 14 of our crackers into that stack, couple it up to the SMR, and you've got a completely green cracking process. So the answer is yes, but it's a way off because the SMR program is, I don't know, online 2035 maybe.
Yes, and probably not. That's very ambitious indeed, given
It is.
Uncertainty of the safety journey, which is one of the reasons that I can see your technology scaling much faster, because it fits within existing safety standards much more conveniently.
Yeah.
Purav Shah asks about the embodied energy of making the turbines. Have you considered that? What are you going to do at end of life with the turbine blades?
Well, I mean, the materials that are in these machines they're readily available. What I would call a sort of low grade aerospace standard materials that are recyclable and are recycled today. So end of life, we're expecting that these materials would be recycled and reused. Bearing in mind, as I said earlier, this stuff doesn't have to leave the ground. It does have to be safe to operate, but there aren't the constraints in terms of recycling and reusing machine materials.
Terrific, thank you. I had a couple more as we've got a little bit of time left. If anybody else has anything on their mind, do post it. Something that I don't think I've seen, but which would be very helpful here, is a sort of market analysis of industrial heat by temperature and volume, or gigajoules, in different sectors. Have you done that? Do you know really what you're trying to...
Yeah, we've done it in a huge amount of detail. We've had independent management consultants go out and validate our assessments. That produced an interesting result in that they came back and said the market was probably twice as big as we thought it was. We've since been off and employed a number of other consultants who were more specialist, I think I would add. And that's brought, I would say, a little bit more colour to that map. The market is huge. Currently, we've identified 40 use cases. There are more than that. So the answer is we've done it. We're treating that analysis of sort of a little bit private to Coolbrook, because it'll be very interesting to our competitors. So it's not information we're readily sharing at the minute, but I can assure you it has been done, and it's been done sort of with 3 different approaches actually, and that's validated the opportunity.
Not wanting to persuade you to give away any of your secrets, are there any particularly tempting temperature bands where you think you're going to get the biggest advantage?
Well,
you don't have to answer.
The answer is it's in that above 700 degrees C temperature range, where electric heaters, resistance heaters, can't deliver the temperature, and there isn't any other alternative. And between 700-800 and I'll say 1200, there's a pretty big opportunity there in the market, and a whole variety of processes, as I said earlier. Yeah,
I agree and understand. Malcolm Brinded is back with his legal hat on, saying, are there competitors working on something similar in China?
As far as we know, not in China. The only competitor we're aware of, and they have shared sort of in the industry their progress, is Siemens, who are working on a rotary cracker, which does work, I'll say, in a similar way to our machine. So there is one competitor who is working on the cracking process. As far as we know, there is nobody working on an air heater to date.
Super. And Gavin Vicknarajar back with another question. has an analysis been conducted into the likely future of UK electricity pricing? Well, Gavin, there have been so many that if you put them all in a pile, you could probably get to the top of the Eiffel Tower without difficulty. Electricity price is currently set by gas price. Do you see this changing anytime soon?
Go on. That's not a subject I'm an expert in. If I believe the press and sort of dialogue that's going on, it is set to come down, but by how much, I don't know. And I guess it'll also depend upon what happens in the world, in Ukraine and Russia and China. So, yeah, go on. I haven't got a really view on that.
The unit cost of renewables seems to be coming down at a fairly steady rate as scale has gone up. The gas price is obviously highly geopolitical, and the nuclear price is artificially high because of the government having to cover itself against all risks. So I don't know. We don't know how that's all going to play out. My guess is that given that CCS is growing so slowly as to be negligible, and there aren't any negative emissions technologies available at scale, then actually a decarbonised future is an all-electric future, and it's a certainty that we are going to be short of electricity. We're just not deploying it at anything like the right scale. So my punt of an answer is that the electricity price is going to rise substantially as we find that demand outstrips supply by a factor of 2 or 3. And at that point, all of the parallel work that we're working on that complements what Rob's been doing about demand reduction is going to become absolutely the forefront of political approaches to mitigation. That would be my punt, but there will be other people on the call with other views. Okay, I think we are very nearly at time, and I think we've got through all of the questions, both easy and difficult. And thank you very much for the many people who've contributed to the discussion there. Rob, is there anything really difficult that we should have asked you that we haven't covered?
Really difficult. No, I mean, one of the challenges for these companies that we are working with is, have they got the power supply to their site? Petrochemical companies tend to already have it. Cement companies, yes and no. It is interesting. I paid a visit to Ultratech earlier this year to look at their cement installation in India, and they've got a huge solar field. They've also got their own generator and coal-powered fire station, and they also draw electricity from the grid. So they've got this interesting supply to the site, which is a mixture of 3 technologies. And they've clearly got enough power supply to their site, because they're growing that to, as I say, up to 30 megawatts of solar panels, which is, I can't imagine what that looks like, but it's going to be a few acres. I mean, at the higher temperatures, there's clearly mechanical design challenges on casings and exhaust systems, trying to just get metals to survive at 1700 degrees C for, hours on end is a challenge. But what I'll say is it can be done. It's just a mechanical design challenge. And we need to work out how we cool it efficiently. And most of the cooling schemes we're examining are recuperative, so the cooling air goes back into the front of the machine, so you don't lose any of that energy as you cool the critical components.
Yeah, I would guess that you've shown us 1,000 degrees already, and so the journey to get from there to 1,600 is going to throw up some challenges, and we'll watch with great interest and keep our fingers crossed that you overcome them as rapidly as possible.
Yeah.
Well, I think with that, I'll draw the session to a close. Rob, thank you very much indeed for this. It's an absolutely crucial area. It's, I think, going to become completely central to how we decarbonise industry, precisely because carbon capture is not being deployed at any rate, and because the electricity supply to make green hydrogen isn't there, then direct electrification of industry is going to turn out to be mainstream. It's underexplored at the moment, and seeing a brilliant innovation like this open up an avenue to what we knew was the hardest problem is, for me, really exciting. Obviously, fingers crossed, and we look forward to peering over your shoulder as the thing grows. So thank you very much indeed on behalf of everybody on the call. Thank you to Susan and Nish, who've been in the background running the session. Thank you very much to the audience for staying with us for the whole hour. And the recording will be released on the website tomorrow, and I think you'll receive an email to send that link. So with that, thank you, everybody, and have a good rest of the day. Bye-bye.
Thank you, everybody.